Blah, 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 blah. Blah, blah. Ah. Number 1 from lecture number 3, homework set 2. On the quarterback one that we're talking about. Okay. So the deal here is, I think, easiest to see if you draw a picture. So basically, you've got this quarterback who's going to throw a football, and the football is going to follow kind of the normal parabolic trajectory. Right? He claims he can throw the ball 183 meters in length. So this is essentially the range in the problem. Furthermore, he claims he can do this by launching the ball at the angle of 30 degrees. So that's this angle we're talking about here, that initial velocity, that's a 30-degree angle. Evaluate the claim, determine the speed with which the quarterback has to throw the ball. So this is one of those cases where you can fall back on the first principles, the x and the y stuff, or we can try and use one of the trajectory equations, right? From the lecture 3. So these equations here, so the two projectile motion equations are kind of what I'm calling the first principles. This is the motion in the x direction. This is always true for a projectile under free fall. It's always going to be moving with this constant velocity equation. And the y direction is always going to be subject to the influence of gravity. It's kind of the same thing, but you've got the influence of gravity here is pulling it down. So that's what pulls the object down under the influence of gravity. But we do have these three kind of shortcut equations. And in this case, since we're talking about range, it kind of begs that first range equation. Okay? So if we look a little closer at this then. So what do we need? We need R, so we're given R is 183. G is always 9.8, negative, but always positive 9.8. We're actually asked for this velocity. That's what the question was. How fast does the football have to be thrown in order to go that distance? And that angle is the 30 degrees we're given. So once I kind of inspect that and look at what the data I'm given, if you want to be really explicit, you can write it all down like this. Right. I haven't been doing it this way, but you could write it that way because all of those are what you need in order to make this equation go. So once I plug all this in, then it's just a matter of doing the algebra. Because I have an equation with just v in it. So I just need to solve this equation. Does that make sense? And so, yeah.
The range wouldn't be in degrees, would it? You mark it, the range is 183 degrees up there.
Here?
Up there when we were writing down these.
Sorry, yes. Thank you. So basically, multiply 9.8, divide by the sine of 60, right? This is going to be 60 degrees. So we get 183 divided by 83 times 9.8 divided by sine don't get the answer I get, make sure that you got your calculator set in degrees. It was a problem a couple people always have here. So I get 2070 when I do that, take the square root. Great. Yeah, final answer would be equals 45.5 meters per second. And here, that's the answer. And the point of this is that that's about how fast a pitcher throws a fastball. So obviously, the football player not going to throw the ball. That football player's a liar. Pants on fire, man. Make sense? Okay. Anything else? Yep.
Number 2, I wasn't quite sure.
Okay, so I can think of 2 ways to solve this problem. That looks a lot like number 1, right? Except because I would redraw the same exact picture. Except I'm not asked for the initial velocity. That's the problem. Right. I'm told this angle is 28 degrees. I'm told this distance is 16.8. Oh, sorry. I am told this speed here is 16.0. So let me double check. This is more complicated than I thought, because it's not going to. Okay. Now I see what's happening. So this is what I would initially put down. I go, what the heck? There's no question, right? Everything's constrained. Well, there's more to it. The problem's not very explicit, but it doesn't actually say that the soccer ball gets back to the ground. In fact, the more I think about it, it kind of implies that the soccer ball is actually above the ground, because that's where the goalie is. So actually, this distance of 16.8 is occurring somewhere here. So the total range is more than that 16.8. I'm not told that total range, which now negates my ability to really use this formula, the range formula. All right, what about the other ones? The other ones involve the height at the center, again, not relevant. The other is time, which is not relevant. So that only leaves me one recourse, is to fall back on those more basic equations, which look like this. And that. So I need to use these equations. All right. Let's go ahead and use them. So what about the horizontal distance? What do I know? I do know x. That's one of the things I'm given. Total x distance or displacement is 16.8. What about v0 in the x direction? Right? X, y. Well, it's this velocity, but only the x component of it. It's this component of that 16 meters per second, right? So that means I need to pull out my trig. The way this is set up, I'm going to use cosine, but a way of kind of verifying that is if I were to redraw this triangle. I know this is 16. This is the angle I'm given. So since the velocity component I'm interested in is adjacent to that angle, adjacent involves cosine. So I know that the formula to use looks like this. And so in this case, I've got 16.0 times the cosine of 28 degrees. So that goes here. 16 times and 28. I get 14.127. And what about time? Do I know time? No, I don't know time, but interestingly enough, I could figure it out if I wanted to. And I probably will, actually. But let's go ahead and skip over here and just continue collecting data. Okay, what about the y? I don't know. Right? That's symbol for. What about the vy? V0y. Well, actually, I do know, right? It's this piece of the triangle. It's the other piece of the triangle. So I could write this down. It's actually the sine, 16 times the sine. Let's go ahead and calculate that. We get 7.5115-ish. Again, t, don't know. G, my good friend, 9.8. All right. I think I've kind of exhausted what I know from the problem. And the only thing that kind of jumped out at me during the whole thing was probably I can figure out t. Let's step back and look at the question again. So what are we asked for? Find the speed of the ball in front of the net. Whoa! So what I am asked for is the speed here. What is this final speed here? Well, just like any speed, this speed has got a vertical and a horizontal component. And if I draw that, it's actually going to be going down probably. I don't know this angle yet. Probably I can figure it out, but maybe we don't need it, so let's pause there. This is what I'm looking for. So if I knew these two pieces, I'd be done. What about this piece? Do I know this piece? Yeah. This would be, I call that Vx, and this is Vy. Because it's final, so it doesn't have the little zero subscript like these do. But the short answer is yes, I know that. I saw a couple of you nodding why. What is this number?
14.
Yeah. It's just the same number, right? That's the same number because parabolas are symmetrical, but that's not the answer we're looking for. I hear a lot of murmuring. That's great. This is what I hear. Constant velocity. Yes, very good. Yay! That's what I'm looking for. So this is constant velocity. The horizontal is always moving with constant velocity. Because this is constant, it's always the same number, right? So I do know this. It's 14, as you already said. Okay, so the only real question is, what is this? And this I start to say, well, maybe I can get it from here because I can write it like this. This is the final velocity over here. I do know the initial velocity, I know the acceleration due to gravity. Only I knew a fourth thing, I could figure it out. It's either y or t. Based on what I was saying earlier, it's probably going to be t. So it would have been useful to figure out how long it takes this soccer ball to go from here to here. And that's, once I step back and think about it, actually that's pretty easy. It goes 16.8 meters and it's going 14 meters per second. So it's going to be just over a second, right? So let's figure out exact. T in this case is going to be Vx divided by V0, 0x, or 16.8 divided by that 14 number. Seven, 11822 seconds. So it takes 1.1892 seconds. And that's the number that sits here, 11892 seconds. Now I look at this data and I say, okay, which equation can I use? And even though I wrote G here, I guess I probably should have wrote A as negative 9.8. So I've got my V's, I've got A, and I've got T. So that equation is going to be the one that looks like this. And final speed in the y direction is 7.5115 plus negative 9.8 times 1.1892. That's a negative number. Let's figure out what it is. That's not right. Negative 4.1426 meters per second. I always like to kind of double check that sign, make sure it makes sense. Yes, it makes sense because that velocity is going down at the bottom, at the end there, right? So this is going across 14.1 meters per second, and it's going down 4.1426 meters per second. So how do I figure out the total? This is Pythagorean's theorem. This comes into play here. So the final velocity in this case is square root of that stuff, right? And that gets the final answer, hopefully. So that is one I would classify as not easy. So when I do this, I get an answer of 14.721 mile answer meters per second. You round down to the three significant digits, 14.7. So that's the answer, and I don't think there's a shortcut through that. So that makes sense. Anyone else? You know, that was kind of long, but that's a good example of one that we have to fall back on the basic equations and do. So, all right. Anything else? Any other question or homework problem?
Can you give us a hint for number 3? The bullet.
Okay, my hint for this is this one's even harder than the one we just did. So don't be surprised if it looks difficult, because it is somewhat difficult. And I hear you. You don't want me to torture you with the entire solution, but I'll give you a little bit of hint. All right. This is how I would approach it. Okay. So I just like this one because it's like CSI. All right. So I won't redraw it because the picture's up here, but it really does help to draw the picture, I think. So basically we're being asked for the height of this bullet. This bullet goes through the window at this particular spot and lodges itself in the wall here, all right? We know the distance between the window and the wall, 6.9. We know the height special about this spot in the trajectory, because we don't really know much about where to stop this backtracking. But the thing we do know is that it happens to be moving precisely horizontal at this point. So this is actually the top of the trajectory. You can imagine it being a projectile in reverse. Right? So, so that said, it feels like I should be able to solve this. It feels like I've got enough information because I've got 2 points on that parabola. I should be able to backtrack it all the way through. So how do you do it? I have to draw it. So here we've got, here's the window, here's the wall. So we know this distance here. This is not a triangle, by the way, even though it looks like I've drawn one. So this is 0.5, this is 6.9. By the way, when I draw this out this way, you can see this is radically out of scale. Right? This is 0.5 meter, this is 7 meters long. So actually this is way stretched out. So that's one thing to notice about this picture. It's way out of scale. Right? But basically the first thing to think about is I've really got two problems. Or, yeah, I've got two pieces to this trajectory. That red piece and the green piece here. So I know a lot about the green piece, actually. The red piece is the part I don't know much about. But what I'm able to do is basically use this interface between the red and the green to backtrack into, see, the initial information about the green is the same as the final information about the red. So if I can backtrack and figure out what's going on with the green right at the start, that also happens to be what is happening at the end of the red. Based on the end of the red, then I can backtrack all the way here. That's kind of in words, the solution method. Now, I've done this problem before, so I know exactly what to do. So I'm not saying that it's obvious, but that's what I'm about to do. So given that, let's call this phase 1. Let's call this phase 2. Now phase 1, well, certainly for phase 2, I'm not going to be using those shortcut equations, right? The red, though, I could contemplate using the shortcut equations because this is precisely the height. The height is one of those equations I'm given, actually. So I don't think I wrote the solution this way, but as I'm looking at this problem, I might actually contemplate using this formula for the red section. So the height in the red section, U0, yes. But that angle, what that angle is referring to, is this angle here. Not sure. I want to figure that out. So, what I would really do is I just fall back on those basic equations. I'm going to have 4 kind of columns here. I've got the x of the red. I've got the y of the red. I've got the x of the green. I've got the y of the green. Okay, what do I know about the x? Do I know this x distance, that red distance, the horizontal distance in red? No, but I do know I want to know it. Right? So I'm going to indicate that by just writing it that way. this is what I want. I guess maybe more traditional, I put a question mark there like I've always been doing. Okay, the initial speed in the x direction. Do I know this? Yes, that actually does happen to be one of the things I know. 340. T? No. Don't know that. But like we saw in the previous problem, that's one of the things that connects these two, so I might want to know it. All right, what about this y distance? The y distance in the red. Don't know it, but it is something I want to know. Right? By the way, notice that D here is from wall to wall, or from wall to window. But H is the height all the way to the wall. So this little gap here is contained in the H. So that makes H be a little bit different, but not that big deal. All right, what about the initial velocity in the y direction? Do I know that? Yes, I do know that. It's 0. Acceleration is negative 9.8. And the final velocity, don't know that. Dang it. I don't know. All right. Great. What about the green stuff? What do I know? X distance, I do know that. 6.9. Initial velocity, don't know that. Time, don't know that. Y, yes, I do know that. It's negative 0.5. Initial speed, don't know. T, don't know. A, yeah, I do know that. Negative 9.8. Here? I'm sorry, what?
So we can do at 40 because the velocity based on the horizontal doesn't change.
That's right. Yep. So, here's how I would say this, although you're saying exactly the right thing, is that, like I was saying before, at this interface, the final velocity of the red is equal to the initial velocity of the green. So what's the final horizontal velocity of the red? It's equal to the initial because it's constant velocity. So another way to write that is the final speed in the x direction is still the 340. It's the same, which is the same as this velocity here. Right? And this velocity here is the same as that velocity there. Those blue arrows are kind of the trick, or the thing that ties the two pieces together. So you're right, I do know this. This is actually 340. And so now the problem starts to cleave apart a little bit, because here I can figure out the time involved in the red. I'm sorry, in the green. I can figure out the time involved in the green. I can push that over here, which means I can figure out this V, which is connected to this V here, which then I can use to figure out the T here, put it here to figure out the X, and figure out the Y. So it's all there now on the board. And then it's just a matter of kind of putting all the pieces together. The rest is algebra, as I like to say. But, promise not to torture you with all that. Looks like that's what you need. Anyone else? That look confusing? Let's see. Anyone else want me to keep talking about it?
You should just solve it.
The guy should just solve it?
Just solve it.
I'll just do it in my head real quick. I can solve it if you want, if you're serious. But yeah, push. You really want me to solve it?
I really want to
Okay,
solve it.
I'll do it. All right, so from here, switch colors again. Purple, so I got left. So here I'm able to figure out t. T is the x divided by v0, in this case 6.9 divided by 340, which is, huh?
0.02029.
29,
0.0292029.
like that, 2029, all right. So that's how long it takes the bullet to go from here to here. I mean, we're calculating the x, but it's also how long it takes to fall, right? So that's the same time it goes here, 0.2029, okay? Okay, given this, I can figure out the initial velocity, the velocity in the vertical direction, how fast the bullet is falling right when it goes through the window. Clearly, we're making an unrealistic assumption that the bullet doesn't slow down at all through the window. But it's going fast enough that it's probably not too radically wrong. All right, so given y, v, t, and a, I'm going to use y v0t minus plus at squared, that formula. So I've still got my negative 0.5 equals v0, which is what I'm looking for. Time I know. Right. So that's a mess, but fortunately it's not quadratic. So that's just figuring out all that stuff. Sorry? What?
Negative 24.631.
So negative 24.631 is the speed, right? So this is the initial speed in the y direction is negative 24.6 meters per second down. So it's 24.6 meters per second down, 340 across. Right. Now, I could figure out what the total speed is using Pythagorean's theorem, but that's a waste of time. I don't actually have to do that. All I need to do is transfer those components of speed back over here. So again, I've still got speed here, but now I know that this is negative 24.61631. Okay. I know time unifies these two columns, so I'll want to figure out the time. But I'm also interested in the y because that's what I'm asked for. So actually I need to figure out both of these things. So I'm going to have to who knows when that stops, but it's going again, so thank you. All right, so lecture number 4 is all about chapter number 4. Chapter number 4 is 3 laws of motion, Newton's 3 laws of motion, but of the 3, the second is by far the most important. It's like 20%, 70%, 10% in terms of importance. It way is much more important. So that's why I called this fourth lecture, called out the second law, because that's really what we're going to be talking about. But it is worth spending a little bit of time to talk about certainly the first and first law of motion. So that's what I do here on the first slide. So this first slide is really just a quick touch on Newton's first law of motion. Newton's first law of motion, he actually ripped off from a guy named Galileo, which is Victor's right history, right? Is that how it goes? So Newton stole this idea from, actually that's not true. Everyone knows Galileo invented the principle of inertia. That was one of his major contributions to the study of physics. And What I'm saying here is that fundamentally Newton's laws are based on the premise that there are two basic sources of motion. The first source of motion is inertia. Another way, it's not exactly the same, but you can also say momentum, right? An object has a certain amount of momentum, and the momentum is determined by a property called inertia. So I think you're more familiar with momentum, just kind of speaking in English. But inertia, does everyone know what inertia means? So every morning when the alarm clock goes off, that's when I experience inertia, right? Inertia is that sluggishness, that, oh my God, do I actually have to get up and start moving? Every object, whether it's living or not, has the same kind of feeling, right? So this Gatorade has a certain amount of inertia, and that inertia is just the property that it resists being pushed around, basically. So this Gatorade bottle has more inertia than this tissue paper, right? So the tissue paper has a small amount of inertia, which means that just with a little tap I can get it to move. But the Gatorade bottle with a little bit of tap, it doesn't hardly move at all, right? So that's what we mean by inertia.
So basically momentum is the force that is putting into motion, inertia is the force that is eliminating it from motion. An object.
Well, technically speaking, neither are force, so we shouldn't really
yeah.
speak of force. But colloquially speaking, you can use those terms. But what I would say is that inertia is the capacity or ability of an object to carry momentum. So the more mass an object has, the more momentum it has when it moves. Right? So a train has a lot of inertia because when you step in front of it, it hurts a lot, right? Whereas if you step in front of a ping pong ball, it hurts much less, even though they could potentially be moving. I mean, the train doesn't have to be moving very fast for it to hurt a lot, right? I mean, the train could be moving like this fast, but you're not going to stop it, right? Because it's so heavy, right? So this idea of heavy is another way to think of mass or inertia, okay? So Galileo, before Galileo, everyone figured, you know, everything moves, that's right, and you kick it and it starts to move, but it always slows down and comes to a stop. And prior to Galileo, the assumption was that stoppingness is intrinsic to the object. The object wants to stop, basically. Galileo said, no, 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 no. The object doesn't want to stop. The object wants to keep moving, actually. It's friction. It's an external entity that is slowing the object down. That slowing down is not intrinsic, but extrinsic. Right? And one of his little thought experiments was kind of what I've drawn up here on the board, is that if you have a ball, and it's kind of, you put it in this bowl shape, it will rock up and down, up and down, up and down. If I just extend the right side of this bowl farther and farther and farther, if there were no friction, you know, if this is like a piece of ice on a smooth bowl or something, it'll go up and down, slosh around, around, around. And Galileo thought, you know, if I lower and lower and lower this, it always comes back up to the same height, but as I extend this, I push that farther and farther out. And so if I were to push this all the way down, starting from here, the object would just go and go forever. And that was one of his ways of kind of justifying this idea of inertia, is that once an object starts moving, it's going to keep moving. And that's really Newton's first law of motion, is that an object in motion tends to stay in motion, an object at rest tends to stay at rest. And so that's how you'd say the first law. Now the first law is not really mathematical, which is why we don't really end up using it in any homework problems. But it does kind of set the baseline for the second law of motion. Okay? The second law of motion is fine. An object tends to move in a straight line with constant velocity, constant speed, unless it's kicked in the shin, right? Okay, well what happens when it's kicked in the shin? That's the second law. Okay, and the second law has to do with force. So as I mentioned here, there are really two things that cause an object to move. One, it's intrinsic inertia. The other is external forces. Okay, and it's the combination of the two that create the trajectory of motion for whatever it is, right? So as I drew up here, a force that is directly opposed to the speed, the velocity, the direction of the velocity, will tend to slow it down, or if it's on the other side, will tend to speed it up. A force that is perpendicular will tend to deflect. It won't actually speed or slow down, it will deflect the motion. And so that's what we'll be talking about in the next thing here. So, in symbols, Newton's second law is there on the right. So the net force equals mass times acceleration. This is the second law of motion. And this is actually pretty easy to understand as well, I think. So this m represents the mass. It's the inertia I was just talking about. So the heavier an object is, the less acceleration it will experience under a given force, right? So if m is big, F has to be big for A to kind of be the same level, right? So these are going to go up and down together. These kind of go up and down opposite to one another, right? And that's really the content of the law. It's pretty simple. The thing that makes Newton special was his understanding of the importance of this idea of acceleration. Now we've just spent 2 whole chapters talking about it, so it feels natural because of the way we've introduced this. But historically, you know, talking about acceleration was something new. And it was really what Newton brought to the table in terms of physical ideas. Everyone was always talking about velocity before that. So even Aristotle, all these people. And so Newton was the one who recognized the importance of acceleration. So I'll leave it there. So that's what this picture represents here. There's the difference between a bowling ball and a basketball or a soccer ball, whatever, is the mass, right? So if I kick the bowling ball, it's going to roll a little bit, but if I kick the soccer ball with the same kind of oomph, right, it's going to go farther than a bowling ball. That's why soccer players don't use bowling balls, I think. I haven't really asked. Well, it'd be cool if, you know, you're chucking a bowling ball into the soccer ring. Soccer ring? It's not a ring. The rink? The soccer rink? Is that what it's called?
So they're playing soccer on ice with bowling balls.
Ice with bowling balls. Now we're talking. Huh. Like, that would be huckling with rackets, too. You gotta have a racket. Okay. The other really important piece to this formula is the left side. So something I haven't talked about yet is this idea of the net force. So up till now, all the examples I've used have just one force, but if an object has multiple forces, and everything really does have multiple forces acting on it at one time, the question is, how do those multiple forces interact with one another to produce the net change in motion? Right? And the answer is they add together like vectors. That's why we spent so much time talking about vectors. Is in chapter 4 we'll be using vectors over and over and over again. Oh my goodness. All right. One common misconception that people have is that if I have 2 forces that are opposing one another, the biggest force wins. Okay? So I think that really comes from, again, our experience with friction, that if I have an object that's sitting here, I've got to give it kind of a certain threshold of pressure before it starts to move, right? You know, I'm trying to push a couch across my living room floor. I can't just use my pinky and just take a longer amount of time. No, I've got to give it a little bit of oomph. I got to overcome something. Well, that's a true statement. I do have to overcome something, but that has to do with kind of the complexities of friction. If we take friction out of the equation, and kind of conceptually that's hard to do because everything we know involves some amount of friction. But what happens is that competing forces, opposing forces don't compete like that. So opposing forces basically subtract. So if I've got 2 units of power on this side, your left, and 1 unit over here, the 2 combined together are basically going to produce a net unit of 1 to the left. The 2 and the 1 subtract from one another. It's not like the 2 overwhelms the 1, it disappears and I've got 2 left. That's not how it works. It's an algebraic subtraction.
Can I work on this? I just heard you say, well, there are multiple forces like opposing. There are always multiple forces on this object.
Yep.
So how possible is it if there's always multiple forces, like many forces all the time? How possible is it for you to have 2 forces opposing one another at the same time when there's multiple forces, hitting that object all the time?
I'm not sure I get your question. So what I'm saying is that an object has multiple forces. Any 2 of those are going to be
When you say
potentially
multiple,
opposing.
you mean like 2?
Well, no. I mean, it could be more than 2. Right?
So does an object have multiple forces, at all times?
I guess the short answer is it totally depends, right? An object doesn't have to have forces on it, I guess. I mean, I was just speaking in general, kind of in everyday life. But if you've got an object floating in space, it's going to have no forces on it at all. Right? And an object that's floating in space will then kind of fall back on Newton's first law because it has no forces at all on it. It's just going to move and move and float forever.
All right, I'm sorry, I'm going to be asking questions because I learned English and the way I learned it. And when you're speaking, what I get is, and I try to ask to clarify, so I hope you know,
You should never, ever apologize for asking questions.
Yeah.
So I absolutely welcome the questions. And every question you have, the adage is someone else has it in the room. So definitely interrupt and ask. I enjoy that. Okay, so we will talk about a little bit more. We'll go through in a lot more detail how to calculate this net force as a vector combination. But that's why I wrote this formula here on the left. So, over the years, this has been really confusing for a lot of students. That when we solve these chapter 4 problems, we're really doing 2 things. It's like we do phase 1 and then we do phase 2, and it's easy for me to kind of skip and mush them together in my explanation. But honestly, what we're always doing is we're doing 2 pieces. The first piece is always basically, this is like a step 0 in a sense when we solve the problem. Step 0 is identify the forces that are acting on the object. That is the first thing we always do. Maybe it's 0 things, but that would be a very boring problem. So usually there's multiple forces, 3, 4, 2, 1, I don't know. That's my step 0 in all of these problems, is to step back and say, okay, the object in question is a sled. The sled is being subject to its own weight. It's being subject to the force of friction. A child is pushing it in this problem. That's 3 things. Or, you go through this cataloging of forces, and then you do this summation based on the vector nature of the forces in order to calculate this net force. And the reason for that is to put it into this formula. So that's kind of the process that we're going to go through in solving all these chapter 4 problems. It's basically, see, I wrote it backward on the board here. It's better well, even there, let me write it the way I'm trying to explain it. We got the vector sum of all the forces is the net unbalanced force in the problem, and the net unbalanced force is what goes in Newton's second law. So this is the basic problem solving technique we're going to use. Start on the left, figure out this. Knowing this, I'm going to put it in here and somehow use this, usually using A. And then once I've got this A, that's where all the chapter 2 and the chapter 3 stuff comes in, because that usually will end up being, oh, I know the initial velocity, now I know the acceleration, I'm given the time, blah, blah, blah. So, that is the plan. What's my next slide here? Oh, okay. So before we jump in, well, let's see if we've got a homework problem. Nice to. See this last one, number 8? Actually 2 I saw up there. We'll maybe do these 2 and then take a break. Okay. So start with number 8. So number 8, there's a car moving with the speed. Here's the car. Moves with the speed. Initial speed of 27 meters per second. Time involved after 8 seconds, the car has slowed. So this is the final speed, right? Final speed of 17 meters per second. Find the magnitude and direction of the net force that produces the deceleration. Right? So we start at 27, end up at 17. We're slowing down this car somehow. So we're applying the brakes. So that's why we're being asked, what's the deceleration? I'm sorry, we're asked, what's the net force that causes the deceleration?